Anytime we have a definite integral that represents an area that's created oftentimes with line segments or other semicircle formulas, it actually creates what's just a common geometric region, like a rectangle, triangle, trapezoid, or even part of a circle. And so instead of using a limit of a Riemann sum, we can simply directly calculate the area just using a common formula. For example, let's say we want to look at the area under the graph of 3, from -2 to 3. And this is just a horizontal line. And so when you think about what the graph looks like, it's just a horizontal line. And when you think about starting at -2 and ending at 3, what's happening is you're just creating a big rectangle. So when you think about calculating that area, again, we don't need any complex equations. We can simply look at it and say it's a rectangle, and we know that from -2 to 3 has a width of 5, and clearly the horizontal line 3 gives us a height of 3 on both sides. So the area here is just going to be 15. Now in this example, again, we're graphing a line, so it's 1/2 x, but now it's from 1 to 4. So we can see what the graph looks like. It is that line going through the origin, slope of 1/2, but because it starts at 1 and then ends at 4, the geometric shape that it creates is a trapezoid. So again, instead of doing any advanced calculus, we'll simply calculate the area to be 1/2. Now the height of the trapezoid, or a distance between the parallel sides, is 4 minus 1, so that's 3. And when you want to calculate how tall they are, they're y values, right? So at 1 and 4, if we plug them into the equation, we can figure out how tall they are. So at 1, that y value there is 1/2, so we'll add the 1/2 in there. And then at 4, when I plug it in, that would be a height on that side of 2. And so now that I've used the formula for a trapezoid, I can put it all together and get an area of 15/4. Now again, our next example is a line, x plus 1, but because the limits of integration go from -1 to 2, it's actually going to form a different type of shape. This time, when I look at the graph and go from -1 to 2, it creates a large triangle. So again, we can just say the area will be 1/2 the base of the triangle, which is 2 minus -1, or 3. And the height of the triangle, when I plug 2 into this, gives me a height, again, of 3. So that means the area of this region, as a triangle, would be 9/2. Now, this last one is probably the most, I should say the least obvious, because when you look at it, it's not linear, right? Anytime we graph, and looking at our previous examples, any lines, right, with x to the first power, we definitely have those nice straight edges where we get those nice geometric shapes. But what we need to recognize about this is that this is a semicircle. So as a quick reminder, just a little review, if you were to think about the basic equation of a circle that's centered at the origin, whose radius is r, that equation is x squared plus y squared equals r squared. Now, when we want to talk about a semicircle, because we definitely want a function, right? Let's say we want to talk about the top half of that. Well, first off, we're going to solve for y, and when we do, we'll take our r squared, we'll subtract our x squared, and then, of course, to get y by itself, we're going to square root it. Now, technically, when you solve an equation, you'd use a plus or minus with that, but because we just want the positive top part here where y's are positive, it's just going to be the square root of that. So anytime you see a positive square root of a number minus x squared, it's describing a semicircle centered at the origin who is on the top half, right? Who's above the x-axis. And this number here, that 4, represents the radius squared. Now, you may also see a situation where it's y equals the negative square root of the r squared minus x squared. That would just simply mean we have the bottom half of that circle. Now, it's definitely going to look like one or the other because we're going to be dealing with functions. And a circle altogether is not a function. So semicircles are going to be the parts we care about and really always looking like this radical situation. So just pay attention whether they're positive or negative. So in our situation here, the radius is 2. We're centered at the origin. We got that semicircle. So because the limits of integration are asking us to go from -2 to 2, it's just looking for the area of this semicircle. So here we're going to take the area of a circle and just cut it in half. So it'll be 1/2 pi times our radius of 2 squared. So in this case, it'll just be 2 pi. Now, sometimes you might get situations that change the lower limit to 0, just as an example, and that would be the situation we want the area from just 0 to 4. And again, if that was the case, you would just simply take 1/4 of the pi times radius squared. So just be cognizant of where those limits of integration are to make sure you have the right amount of the circle. Now, the next thing we need to discuss is signed area, because obviously as we're starting to look at more and more regions under curves, they don't always exist above the x-axis. So here, as we can see, I have different pictures illustrating area where part of the graph is above the x-axis and part of it's below. Now, what we have to understand, of course, is that any area above the x-axis is positive, and any area below the x-axis is negative. And one way to think about this is that when you're doing the calculations, the areas above the x-axis have positive y's, and the areas below the x-axis have negative y's. So as you're integrating along the x-axis and you do those geometric calculations, you end up using positive measurements here, negative measurements here, and that results in our area measurements having positive and negative signs. Now, it's important to understand, however, how they interact. When you have this region here and this region here, and you simply calculate the area, because this works out to be a positive number and this one will be a negative, for instance, you don't get the overall area in blue. Okay, you don't get that. What's happening is the negative area down here cancels out some of the area here. So in this example, we have a big positive area and a little negative area. So if I was to calculate what's the area from 0 to this number A, okay, we'll just call this the graph of f, what would happen is I would get this big positive number and then a little negative number canceling some out, but overall, because there's more positive area than negative area, it would work out to be a positive number. Now, the opposite is true in this other picture, right? We have a big negative area and a little positive area. So again, if I was to calculate the area from 0 to A under the graph here of f, what's going to happen as I put this together is we're definitely going to have, like I said, a big negative and a little positive here to cancel some of that out, but overall, it's going to be a negative value. Now, our last example shows some symmetry, okay? So that means that when we look at this situation, we have an amount of positive, but the same amount of negative area. So if you were to sit and do the math and do the calculus and say, what's the area from 0 to A under this graph, what would happen is this amount above and below, being both positive and negative, cancel each other out. And the value of the definite integral would actually work out to be 0. Now, there are definite, applications in calculus where these definite integrals, you want to have the positives and the negatives, and this is fine, right? There are things that are modeled, like velocity, for instance, that have different signs based on what you're doing. However, there's other situations, for instance, like calculating distance, where you don't want that. So we do want to have abilities to cancel out and deal with negatives and maybe instead say, what is this overall geometric area no matter where it is? So the next step we have to talk about having understanding signed area is, how can we use properties to adjust these when needed and how to deal with them? So let's talk about those properties of the definite integral, just to make sure we understand how area works and how we can manipulate and do different things with them. So the first one is kind of obvious, right? We have the area under f along the x-axis, but we're going from A to A, and that simply says that the width of this area is 0, right? There's no distance. There's height, right? But we're not traveling along the x-axis at all. So clearly, if you have a height times a 0 width, your area is going to be 0. Now, this may seem like a strange example of something that may show up, but you'll see later on when we look at things like accumulation functions and you're evaluating them, this thing does definitely happen. Now, our next property is an important one to help us deal with negative area, because again, at times we may want negative area, but other times we may want to get rid of it. One way to do that is to take an integral, right? So we have the definite integral of f of the area from A to B, but if we simply take those limits of integration and flip them, then we actually get the opposite sign. Now, a way to think about this, of course, because you're flipping your limits of integration, is to say that instead of going the normal left to right in an increasing way along the x-axis, we're going from right to left. We're kind of going the opposite way. We're going the negative direction along the x-axis. So a way of thinking about it is that while we may be above the axis, for instance, if we have the direction going the opposite way, it's like having negative axis. So by taking a definite integral and just flipping your limits of integration, the calculation will give you the opposite number. And like I said, if you're in a situation where you need the opposite sign, maybe you don't want negative area, this is a way to deal with it. Now, another important reminder, and we've seen this before, is that like any integral or even derivative or limit or even sum, if you're multiplying your expression by a constant, you can go ahead and just make that calculation and multiply the constant. As always, it just goes along for the ride. Another reminder that we've definitely seen before is that if you're doing a definite integral of the sum or difference of two different curves, just like limits and derivatives and summations and even antiderivatives, you get to do each one separately. So when you're calculating the definite integral of some stuff plus or minus some other stuff, you can separately calculate the area under the first part, calculate the area under the second part, and then add or subtract those different values. Now, the last property that also comes in handy when maybe dealing with wanting to change parts of things is this property here. What it says is that we have some value c that's somewhere between a and b. It's in that interval. And so if I'm looking at the entire area from a to b under the graph, if I wanted, I could instead calculate the area just from a to c under the graph, and then separately calculate the area from that number c to b. And as long as where I stopped here is where I start here, right, it will end up being the entire area from A to B. It just kind of lets you do each piece separately. Now, in particular, looking at this and this property, the idea that you can flip limits of integration and break things up kind of goes back to our situation here. If I was looking at this situation, for instance, and I wanted to know the exact overall area of the blue, right? I don't want to worry about the positive, negative canceling out. I really want all of that area. What I could do here is I could just integrate the first part straight up, and just get that number. It's a nice positive number. Then separately integrate this part of it below, but go backwards, right, by flipping those limits of integration. And therefore, it would make this number a positive number. And then when I put them together, I get that overall area. So that's kind of where these properties overall can kind of help us manipulate different things depending on what we want to calculate. Now let's talk about using the properties and the kind of questions we're going to get. So for example, there might be situations where we're given different values of different integrals, right? Different areas under a couple graphs over different intervals. And we want to use these numbers and values that we know to calculate some other different integrals. So for instance, here we know the area under f from 1 to 3 is 5. The area under g from 1 to 3 is 2. The area under f from 3 to 7 is 3. And the area under g from 1 to 7 is 10. That's kind of our given information. So knowing that, I want to calculate the area under the expression f minus g. Well, like we saw before, we can do each one separately. So what happens here is we actually end up doing the area from 1 to 3 under the graph of f, and then we subtract the area from 1 to 3 under g. So again, we can just kind of do each one separately. So the area under f from 1 to 3 we know to be 5. And then the area under g from 1 to 3 we know to be 2. And it says f minus g, which means we'll subtract that to get a total area of 3. Now in our next example, we have the same thing, but this time we also have multiples. And as we said before, they simply go along for the ride. So what's going to happen here is we're going to double the area from 1 to 3 under the graph of f. And then we'll add on 6 times the area from 1 to 3 under g. So we're going to pretty much use some of the same numbers we did before. So here, we know the area, again, from 1 to 3 under f is 5, but we're going to double it. So it's going to be 2 times 5. And then we add on 6 times the area under g from 1 to 3, which we know to be 2. So when we take 10 plus 12, that's total value here will be 22. Now, sometimes we see situations like this, again, using the same information, where we need to be a little more clever and think very carefully about how we're doing our work. So in our first one with C, we're looking at the area from 7 to 1 of 4 times f of x. Well, right away, because I see the 4, I know I'm going to multiply 4 times that area. But what I notice is that I'm going backwards. Instead of going from left to right along the x-axis in a normal ascending way, we're actually going from right to left. We're going from 7 to 1. So what that means is that whatever this integral is, it's equal to the opposite, so I'm going to have a negative, of going from 1 to 7. Now, because I'm looking at what the area under f from 1 to 7 is times negative 4, I just need to figure that integral out. But I actually don't have that information, right? When I look at the top, they didn't tell me the area under f from 1 to 7. But what they did do is tell me the area from 1 to 3, and I have the area from 3 to 7. So when I think about using that other property, the idea that you can break them up and do separate pieces as long as they fit together, I can actually add the area from 1 to 3 together with the area from 3 to 7, and since this ends at 3 and this starts at 3, it kind of connects together, giving me the entire area from 1 to 7. So the way this is going to work is I'm actually going to take negative 4 times the integral from 1 to 3 under the graph of f, and then add on the integral from 3 to 7 under the graph of f. So when I put all those pieces together, because that is the information I know, I'm going to take negative 4 times our first area, which again the area is going to be 5, plus the area from 3 to 7, which is 3. So in this case, it works out to be negative 32. Now, it's important to understand because our answer is negative 32, you might think, oh, well, whatever this is, it's a region that lies under the x-axis. But actually, it's not. It actually lies above the x-axis because the reason the answer is negative is because my limits of integration are going backwards. If you're going backwards, you already have that negative x field to it, so the y's must have been positive, which means this negative 32 answer is saying this region was above overall in the x-axis, and we simply went backwards. Now in our last example, we're taking 10 times the area of g of x, but we're calculating that area from 3 to 3. So this is an obvious situation where this area has no width. So the answer is 0. Now another situation you might run into is the idea that we're going to be given a graph based on line segments and semicircular sections, and that just simply means that without a calculator, we're going to have these sort of graphs to evaluate areas, and we're just going to again use our geometry. Now what's important to realize, of course, is our limits of integration. We want to make sure we're going the right direction and know where we start and stop, but also paying attention to these geometric shapes and whether they lie above or below the x-axis. So it is going to be doing basic geometric formulas, but it's our job to recognize when we want to put negatives in there or make things positive. So in our first example, we're going from -2 to 5, which means we begin here at -2 and we calculate the area under this curve all the way until we finally reach 5. Now when we do that, we see 3 different shapes. Okay, so beginning at -2 up to 0, this is a triangle. From 0 to 1, we have what looks like a quarter of a circle, and then from 1 to 5, we have a semicircle. Now, I'm going to go ahead and do those 3 different pieces separately and use those geometric formulas, but what I need to do is make this triangle and this quarter circle negative, because as I'm going from -2 to 5, these lie below the axis, which means those technically have negative y values, they're negative area. So when I do my calculation here, I'm going to start out with my negative triangle down here, so it'll be -1/2. It's got a base and height of 2 and 1. So that gives me my negative triangle. Then when I get to my quarter circle, because it's below the x-axis, I have to make it negative, and that's going to be 1/4 times pi, and the radius here is 1 squared. And then when I get to the semicircle, now I add it, because the semicircle is above the x-axis and is a positive area. So that's going to be 1/2 pi times its radius of 2 squared. Now, obviously, without a calculator, we don't expect to be perfect with those numbers. We just clean them up as best we can. And here, when you simplify the numbers and put them together, we're going to end up with -1 plus 7 pi divided by 4. Now, in our next example, we're looking at the area under the graph from 0 to -6. So right away, what strikes me is that we are going backwards. We're going from 0 to -6. We're going the opposite direction than we normally do. So we're going to be going right to left. So that means, of course, geometrically, I'm starting at 0, and I'm calculating the area down here, and then the area down here all the way up till I get to 6. Now, again, if you glance at the graph, it would appear these are both going to be negative triangles because they're below the axis. But I'm going the wrong direction. So because I'm going backwards, right, not the normal ascending way, that changes the sign. So when I do the geometry here, what I'm actually going to do is make this a positive triangle and make this a positive triangle. Because even though they lie below the axis, I'm going backwards and I have to adjust the sign. I have to take these triangles that normally would be positive and make them opposite, right, make them positive. So when I do my calculation, I'm going to start with my first triangle here from 0 to -2 and call it positive 1/2 2 times 1. And then when I get to the second triangle, I'm going to add on the 1/2, and this has a base and height of 4 and 2. So I end up actually with an overall positive area, because while it's below the x-axis, we're definitely going backwards. So when you put all those together, you end up with an answer that's a positive 5. Now for our last example, we have a really common error that happens a lot with these sort of questions. Now clearly we're doing the area under the graph of f from 5 to 7, so it's going to be this region over here. And if I go ahead and sketch what that looks like, that's pretty much going to be some sort of triangle. However, I have a +3. Now the common error that happens a lot is that sometimes students will find the area of this triangle and just add 3 to it. That's not what's happening. What we have to remember from graph transformations is that when you take a function and add 3, it takes this red triangle here and shifts it up 3. Now physically what that does as far as area is it basically puts a big rectangle underneath it, a rectangle who's 3 tall. So if you want to think of taking this graph and physically moving it up, that is one way to do it. We're taking the triangle and adding a rectangle underneath it. But I will say, if you don't want to worry about redrawing or thinking about it visually different, you can simply break this up and do each piece separately. We could say we're going to find the area from 5 to 7 under the graph of f, and then separately add on the area from 5 to 7 of 3. Now, clearly here on the left side, we're referring to this graph, and this right here will be that triangle. So this part of it will be the 1/2. It's got a base of 2 and a height of 4. But when I come over here, this is simply the definite integral from 5 to 7 of 3. And just like our first example, this is describing a horizontal line 3 from 5 to 7. And that, again, is physically a rectangle whose width is 2, and again, whose height is 3. So if we think about it that way, we'll easily get the correct answer, because again, we're adding a rectangle underneath it. So when we put all that together, we're going to get a total area of 10.